Hi, this is David Bates. This is our final video update for Team 6, the Remote Acoustic Sensor team. Since our last video update, we have been working hard on preparing for Demo Day. We've been finalizing our plans for this summer, as well as working on the final hardware and software design. For this summer, we plan on performing our full functional testing and environmental testing as required for our Nano Lab. What we've been doing this past semester since March, the beginning of March with the first video update, we have been working on our payload safety package and providing our periodic updates to ASU New Space NanoRacks. To further discuss the individual subsystems, I'm going to hand it off first to Roland Lizana.
Hi, my name is Roland Lizana. I am the mechanical designer for the RAS team. Over the past few months, I have been working on the EM1 build, which is our engineering model, in which we're going to use to do our fitting, testing, and initial engineering review, get the subsystems working and everything. I've been able to print all the parts out of 3D material, FDM, and I fitted, fabricated, filed, milled, looked at tolerances, and finally got a housing built, which I shipped to Logan and David. So Logan's going to talk about the housing and the electrical system being integrated into the house.
Thank you, Roland. I'm Logan Sisca, and I am the electrical hardware lead for the Remote Acoustic Sensor Nano Lab. During the past 2 months, we've been hard at work finalizing the design for the electrical systems in the Nano Lab, producing those designs through both schematic capture and printed circuit board layout in Altium, and then having PCBs fabricated and finally populating them with our soldering equipment in-house. I have a circuit board here, the Remote Acoustic Sensor board itself. This is the heart of the Nano Lab. It consists of the array of phototransistors that measure the light modulations produced by the honeybees in our experiment package. And it also has an analog to digital converter and supporting circuitry that allows us to read the output voltages from those phototransistors and actually collect data for use throughout our rocket launch. Now, as David and Roland mentioned, we will be integrating these boards into the mechanical housing that Roland has designed and constructed. And following Demo Day this summer, we'll have a rigorous series of tests, both electrical tests and mechanical tests, to ensure that our payload can withstand the rigors of spaceflight. So with that, I will pass it off to Bryan Trinidad to discuss the software.
Hello, my name is Bryan Trinidad, and I am writing the code for our payload using Python. The software is initialized and a save file is created, storing the RAS collections along with the date and time associated with each collect. The save file is located on the SD card mounted to the Raspberry Pi. The SPI bus is used to interface the Raspberry Pi with our ADC. All 12 channels of the ADC are used and scanned in ascending order using the programmable Auto 1 mode of the ADC. There are 2 files for the software named ADS7952 and data acquisition. The ADS7952 file contains SPI and ADC read and write parameters. The data acquisition file calls supporting libraries, configuring the hardware SPI, creates the save file, and prints the values collected. Code testing is done with assistance from Logan. I compile and send the software to him, and he runs the software with the hardware and sends back notes so I can make necessary updates. I believe we're on track to have a finished payload for this year's fall launch. Thank you for watching.